0. You can think about that, why that is the case. So these field configurations can be rather complicated and can be very interesting, and each one has its own applications. Are dipoles rare in physics? Not at all. In fact, they are extremely common. You cannot avoid them. Remember last time I told you, if you have a spherical atom or you have a spherical molecule and you bring that close to a charge, let's now think of it, you bring it in an electric field. It's another way of saying the same thing. So we have a nice spherical atom or a nice spherical molecule, and we bring it in an electric field. The electrons want to go upstream the electric field vectors. They go against the direction of the electric field. And the positive charge wants to go in the direction, wants to go downstream. And so, what are you going to do? The electrons will spend a little bit more time on one side of the nucleus than they would in the absence of that electric field. And therefore, you are, through induction, turning that atom, turning that molecule in becoming a dipole. If you have a little bit more charge on this side, averaged over time, you have the same amount of extra charge plus on that side, averaged over time. So you make dipoles very often, whether you like it or not. And later in this course, we will learn more about the polarization of atoms and molecules creating dipoles when we talk about dielectrics. And you will see that it will have can have an enormous impact on the properties of the material. Could I make you a dipole here in class? Oh yeah, that's very easy. To make one of non-conductors is not so easy in class. To make one of conductors is very easy. And I'm going to do that with these two spheres that you have. Look at these two metal spheres. Conductors, free electrons, it's very easy for them to move. And I'm going to bring this rubber rod, which I will rub and becomes, I think, negatively charged, if I remember correctly, and I will bring that, say, close to these two, which are touching each other. So here is this one metal sphere, and here's the other metal sphere, and here comes the rubber, negatively charged. What's going to happen? The electrons want to go away, so this becomes negatively charged, and therefore this remains a little bit positively charged. For every one electron that is excess here, when I start it's neutral, there will be a positive excess there, because charge is conserved. You can't create charge out of nothing. And now what I do, while this rubber is still here, while that rubber rod is there, I separate them. So here they're in contact with each other first. They have to be in contact. Wow, we get some visitors.
Don't be late. That means you, pretty boy.
I'm impressed. Thank you. So what I do now is, while this rubber rod is still in place, I take them apart. And when I take them apart, this negative charge is trapped, and this positive charge is trapped. And so I have thereby created negative charge on this one, positive on this one, and it's equal in magnitude, so I have a dipole. What I want to demonstrate to you is that indeed I have positive charge here and negative here, that there is a difference in polarity between these two, and that's the way that I will do the experiment. I will not show you that the amount of charge is exactly the same on each, which of course it has to be. So let me give you some better light, or we have to get the view graph off, the overhead. You see there for the first time an electroscope. We discussed it last time. It is a piece of aluminum foil, very thin, with a metal rod next to it. And when I put charge on the rod, it will also go onto the aluminum foil, and they will repel each other, and so the aluminum tinsel will go to the right. And the more charge there is on it, the farther it goes to the right. So let me first put these two together, make sure they are completely discharged. And now I'm going to bring these two into an electric field, which is produced by this rubber rod. have to rub with the cat fur, and I believe it was negative. But if you'd never have to remember whether it's negative or positive, of course. That is not so important. What is in a name, after all? But it happens to be negative. Okay, so now we go here. I bring it here. I hope that no sparks will fly over, because that ruins the demonstration. And now, notice what I do. While the rod is here, I separate them. So as I was holding it there, things were going on in there that you and I couldn't see. But the electrons, the rubber rod is negative, electrons were shifting in this direction, and this is now positive and that is now negative. If I take this one and I touch it with the electroscope, you clearly see that there is charge on this. How can I show you now that there is charge of different polarity on the other one? Well, the way I will do that is I will approach this electroscope by bringing this sphere very close to it. And if this charge is different than the charge that is on it, the electroscope will, the reading will become smaller. And why is that? Why will the reading become smaller? Well, here is the situation of the electroscope now. And here is that ball that you see on top. This is upside down there. If this is all negative, that's why it is apart. If now I approach this here with an object which is positively charged, and I claim that this one now is positively charged because this one was negatively charged, then electrons are afraid of the positive charge, so more will go. Excuse me, electrons love the positive charge, so the electrons want to come to the positive charge, so these electrons drift down again. And so if they come down, fewer will be here, and so you will see this. If, however, I put here a negative rod, then the electrons which are here want to go further away, they will stream up, and therefore the reading will become larger. So you can always, through induction, test what the polarity is of your charge. Let's hope that this one is still holding its charge while I was talking. So I claim now that if this polarity is different, and if it's still there, when I approach the electroscope, come very close, that the reading should become a little smaller without even touching it. Let's see whether that works. You see, it goes down. You see, it goes down. It goes down. So through induction, I have demonstrated that this has indeed a different polarity from this one. If I approach it with this one, it would go further out, unless it already is at a maximum. Let's try that. You see, it goes further out. So not only have I demonstrated that I created a dipole, but you've also